Why this matters. This project exists because accountability requires evidence, and evidence requires method. When powerful institutions fail the people they are meant to protect, the public record becomes the last line of defense. Not opinion, not allegation, the record. Computational analysis of that record is not an abstraction. It is not an academic exercise performed at a safe distance. It is an act of civic responsibility. The decision to build a pipeline that measures, validates, and discloses its own errors is itself a statement about what justice demands. Freedom depends on the ability to see what happened, not what someone says happened, not what a press release claims, what the documents show. Justice depends on the willingness to prove it, to subject every method to scrutiny, to publish every error rate, to retract what cannot be defended. The pipeline documented in this series does not advocate, it does not accuse, it measures, it validates, it discloses its own errors. Standing for freedom and justice means insisting that the truth is knowable, that the methods used to find it can be tested, and that the people doing the work will tell you when they got it wrong. That is what this episode is about. Before we begin, here's what this episode covers. 0.84, the minimum F1 score required for entity resolution before any finding is presented as evidence. Below this line, the machine's answers are not trusted. This episode is about the method, how we know what we know, and how we know what we got wrong. The Daubert Standard, from Daubert versus Merrill Dow Pharmaceuticals, 1993. 4 pillars that determine whether computational analysis can survive federal court. 5 quality gates the pipeline must pass. 46 anchor entities and 50 calibrated dates used as fixed reference points in a corpus with no answer key. What corroboration found? 5 timeline dates were wrong. 2 observations were retracted. The pipeline hallucinated Poland from a blank form and Krakow from a document header. And the N212JE tail number recycling was caught by external research, not by the pipeline itself. The computed results: 125,620 communities detected. 519,000 entity clusters resolved, 889 temporal breakpoints, and Chow-1 estimates 63.7% of all entities have been surfaced, meaning over 468,000 remain unseen. 0.84, the line between computation and evidence. .84. This is not a probability. It is not a confidence score. It is a threshold, the minimum F1 score for entity resolution. F1 is the harmonic mean of precision and recall. Precision: of the entities the pipeline linked together, how many were correct? Recall: of the entities that should have been linked, how many did the pipeline find? Why a harmonic mean instead of a simple average? Because the harmonic mean punishes imbalance. A system with 99% precision and 1% recall gets a simple average of 50%. It gets an F1 of 2%. The harmonic mean exposes systems that are good at one task and useless at the other. If the pipeline cannot correctly link and separate entities with at least 84% accuracy, its outputs are not presented as findings. They are flagged, reviewed, and held. Below this line, the machine's answers are not trusted. In 1993, the Supreme Court decided Daubert versus Merrill Dow Pharmaceuticals. The question was simple: when does expert testimony qualify as science, and when is it just opinion dressed up in technical language? The court established 4 pillars. First, the methodology must be testable. It must be possible to prove it wrong. In this pipeline, that means deterministic reproducibility. Given the same documents, the same random seeds, and the same parameters, the pipeline produces identical results every time. If you run it and get a different answer, something broke. That is testability. Second, the error rate must be known, not estimated, not low, not negligible, known, computed, documented, and published alongside every finding. This is the pillar most projects fail. They present results without ever measuring how often those results are wrong. Third, the methodology must be peer-reviewable. Every core algorithm in this pipeline, Leiden community detection, Splink probabilistic linkage, PELT change point detection, is published in peer-reviewed scientific literature. The methods are not proprietary. They are not trade secrets. Anyone with the technical background can evaluate them. Fourth, the methodology must be generally accepted. Bayesian probability, expectation maximization, graph-based community detection. These are standard tools in computational forensics, not experimental techniques. This project was not designed for court, but the Daubert Standard is not just a legal test. It is a minimum standard for intellectual honesty. Findings that cannot survive legal scrutiny should not survive public scrutiny either. The pipeline enforces 5 quality gates. Each one exists for a specific reason. Gate 1, Entity Resolution. F1 must exceed 0.84. Why this gate? Because every downstream analysis, every network, every community, every temporal pattern depends on correctly linking records to real-world entities. If the linkage is wrong, everything built on top of it is wrong. This gate is designed. The Splink framework is built and tested on sample data, but it has not been formally evaluated at production scale. Gate 2, Network Modularity. Q must exceed 0.30. Why? Because a modularity score below 0.30 means the community partition is not meaningfully different from random. The algorithm would be finding structure where none exists. This gate is now testable. Leiden community detection partitioned the entity network into 125,620 communities. Gate 3, Document Retrieval Recall between 75 and 80%. Why a range? Because 100% recall is impossible in a corpus this degraded by OCR errors. 75 to 80% is the realistic ceiling, designed but not yet validated. Gate 4, Calibration anchor alignment must exceed 85%. This gate tests whether the pipeline's temporal outputs match known reality. 50 dates from the calibration timeline were checked. 5 were wrong. Corroboration caught them. Gate 5. Compound error propagation must remain within acceptable bounds. This is the metagate. Even if each individual stage passes its gate, the accumulated error across all stages could exceed tolerance. The model exists. It has not been fully executed. No finding passes to the public without clearing all 5. Where a gate has been tested, the result is stated. Where it is pending, that is stated too. Source check. The calibration framework rests on anchor variables, fragments of verified reality injected into a system with no answer key. 46 corporate entities confirmed through public filings. New York DOS, Delaware Division of Corporations, Open Corporates, USVI Records. 50 dates from the calibration timeline, sourced exclusively from government and court records. 5 principal officer relationships: Indike, Kahn, Visosky, Maxwell, Kellerhalls, confirmed through DOJ filings and the NYDFS consent order. FedEx records bound the shipping timeline to 2001 through 2005. Deutsche Bank records bound the financial timeline to 2013 through 2018. These anchors are stored in an immutable calibration table. The pipeline does not know they exist. This is the critical design principle. The anchors are not training data. The algorithms were never optimized to find them. If the pipeline correctly recovers these known realities without being told they are there, the methodology is validated. If it fails to recover them, the methodology is falsified. That is what testable means. The core problem. There is no answer key. No pre-existing dataset tells the pipeline which entities are correctly linked. No labeled set confirms which relationships are real. No verified list identifies which temporal change points are genuine structural breaks versus noise. No ground truth defines which community memberships are correct. Every algorithm in this pipeline produces outputs that look plausible. They form clusters, they detect patterns, they find change points. And every one of those outputs may be systematically wrong in ways that are invisible without external validation. This is a fundamental problem in unsupervised analysis. The machine has no teacher. It has no exam with a known answer sheet. It is pattern matching in the dark. And the danger is not that unsupervised systems fail obviously. The danger is that they fail quietly. They produce clean-looking outputs, neat clusters, confident scores, plausible timelines, and nothing in the output tells you it is wrong. This is the problem that calibration solves. The solution: anchor variables. Verifiable fragments of reality, corporate hierarchies, biographical events, financial flows, injected into the system as fixed calibration points. 46 corporate entities confirmed through public registries. Jeggy Inc., Delaware filing number 3284812. NES LLC, DOS number 2288572. Southern Trust. Butterfly Trust, not a registered entity in any corporate database, but a trust instrument confirmed through the NYDFS consent order. Each of these anchors was verified independently outside the pipeline against government registries that the algorithms never access. 50 calibrated dates from primary government sources. The non-prosecution agreement was signed September 24, 2007, not June 30th as initially recorded. The NYDFS consent order was July 6, 2020, not November 2019. 5 principal officer relationships. If the pipeline correctly identifies Indike as an attorney and Kahn as an accountant without being told, it passes. 2 temporal boundaries. FedEx shipments from 2001 to 2005, Deutsche Bank records from 2013 to 2018. 400 predictions per pipeline stage, sampled across the full confidence spectrum, not just the ones the machine is most sure about. 3 confidence strata. The high confidence stratum, predictions above 90%, verifies true positives. These are the easy cases. The machine is confident, and we check whether that confidence is warranted. The boundary stratum, 45 to 55%, detects threshold sensitivity. These are the predictions the machine is least sure about. They sit right on the decision boundary. Small changes in the threshold would flip them from positive to negative. If accuracy collapses in this zone, the threshold is fragile. And the low confidence stratum, below 10%, catches false negatives. The machine said no. Was it right to say no, or did it miss a real connection? Each set is reviewed through blinded manual verification. The reviewer does not see the algorithm's prediction while making their judgment. Then bootstrapped 1,000 times to generate 95% confidence intervals for precision, recall, and accuracy. This is BBCCV, Bootstrap Bias-Corrected Cross-Validation. The bias-corrected part matters. Without correction, standard cross-validation overestimates performance on small datasets. The Bootstrap compensates for this. The selective verification paradox. If you only review the predictions the machine is most confident about, its accuracy looks perfect. Of course it does. You are measuring the machine's best work and ignoring everything else. This is the most common validation error in machine learning systems, and it is the most dangerous one because it produces a number that looks rigorous, 99% accurate, published in the methods section, cited in the conclusions, and completely misleading. The fix is stratified sampling across the entire probability spectrum, high confidence predictions, boundary predictions, the ones hovering right at the decision threshold, and low confidence predictions, the ones the machine almost discarded. The Bootstrap protocol in this project samples all 3, because a system's true accuracy is defined by where it fails, not where it succeeds. Entity resolution calibration, the foundational gate. Splink, a probabilistic record linkage framework built on the Falegy-Sunter model. It calculates the probability that 2 records refer to the same real-world entity based on matching and non-matching weights trained through EM, expectation maximization. Step 1. Inject calibration probes. Known entity clusters, groups of records that definitely refer to the same person or organization, are inserted into the data. The algorithm does not know they are calibration probes. It must discover the linkage on its own. Step 2. Clerical review. 400 record pairs, sampled across the entire match weight spectrum, reviewed by a human analyst. Critically, the algorithm's prediction is hidden during review. This prevents automation bias, the same principle behind double-blind clinical trials. Steps 3 and 4. Isolate where the algorithm was wrong, then sweep probability thresholds to find the value that maximizes F1. Step 5. Lock the threshold and apply to the full corpus. Result: 519,000 clusters resolved from 2.38 million entities. The Nadia Marcinkova test. Nadia Marcinkova, a named co-conspirator in the Epstein case. Her name appears in the corpus in 48 different forms: OCR degradation, inconsistent formatting, partial names, even property record artifacts. 8 representative variants are selected as calibration probes. 48 records, one person. The entity resolution system must consolidate all 48 into a single canonical entity. If it fails, if even one variant remains separate, the pipeline has a recall problem. False negatives, missed connections. But the opposite error is equally dangerous. Over-merging, collapsing records that belong to different people into a single cluster. The test for this: examine the internal edge density of each cluster. If a cluster holds together because of a single low-weight edge, not a dense web of connections, it is probably a false merge. Undermerging is detected through Splink's unlinkables chart, records that cannot surpass the matching threshold no matter what. These are fragmented identities the system has given up on. Both errors matter, and both must be measured. The pipeline. You have seen this DAG before in episode 2, but now it has checkpoints. Every stage where a quality gate applies is marked. After named entity recognition, gate F1 must exceed 0.84. After entity resolution, same gate. After network community detection, gate modularity Q must exceed 0.30. After temporal change point detection, gate at least 85% of detected breakpoints must align with calibration anchors. And at the end, the compound error gate. Upstream errors propagated through all downstream stages must remain within acceptable bounds. The gates are not suggestions, they are hard stops. If a gate fails, the outputs from that stage are flagged, held, and reviewed manually before they can propagate downstream. This is the pipeline stage segment. In earlier episodes, it showed you which stages are complete. In this episode, it shows you where the machine is checked. The N212JE lesson. The tail number N212JE was used for two different airframes. From May 2013 to August 2017, a Gulfstream G4 serial number 1085. After a gap of several months, from January 2018 to March 2021, a Gulfstream G550, serial number 5173, a completely different aircraft. Think about what this means for the pipeline. It sees a tail number, it creates a node. Every flight log entry tagged with N212JE gets linked to that single node in the entity graph. The pipeline has no mechanism to detect that the identifier was recycled. It sees continuity where there is actually a substitution. A different airframe, different avionics, different maintenance history, but the same 6 characters on the tail. This was found by corroboration, external FAA registry research, cross-referencing tail numbers against serial numbers and registration dates, not by the pipeline, not by any internal validation check. No amount of internal consistency testing would have caught this, because internally the data is perfectly consistent. One tail number, one node. The error is invisible from the inside. This is a category of error the pipeline cannot self-detect. False continuity from shared identifiers. And it is why calibration must include external cross-references, not just internal consistency checks. The corroboration report. 6 parallel research streams, each cross-referencing pipeline outputs against public records. 7 corporate entities checked against state registries. All 7 confirmed. 1 DOS identifier clarification needed. 11 tail numbers checked against the FAA. 6 confirmed as Epstein aircraft. 5 conclusively not Epstein. 1. N212JE revealed the tail number recycling. 8 named associates checked, 6 confirmed. 1. Dave Limmer, refuted as an OCR artifact. The actual second pilot was David Rogers. 1. Lauren Quine, corrected to Lauren Quintner, an OCR truncation. 18 calibration dates checked, 5 were wrong. The non-prosecution agreement, jail sentence start, Jeffrey v. Maxwell filing, USVI settlement, Deutsche Bank consent order, all corrected. Observation 1. The Robert Crumb FedEx shipment, fully refuted. Crumb has lived in France since 1991. External verification is not optional. It is a pipeline component. 5 calibration dates were wrong. Think about what that means. These are not obscure data points. These are calibration anchors, reference points the entire temporal analysis is measured against. When the reference point is wrong, every measurement taken from it is wrong. The non-prosecution agreement, recorded as June 30th, 2007, correct date September 24th, 86 days off. Epstein's jail sentence start, recorded as July 1st, 2008, correct date June 30th, 1 day off. He pleaded guilty and began his sentence on the same day. Jeffrey v. Maxwell, recorded as January 2nd, 2015, correct date September 21st, 262 days off. Not a rounding error, not a typo. 262 days. The USVI v. JP Morgan settlement, recorded as January 17th, 2023, correct date September 26th, 252 days off. And the Deutsche Bank NYDFS consent order, recorded as November 2019, correct date July 6th, 2020, 8 months off. Every anchor that was wrong has now been corrected, but the lesson is not the correction. The lesson is that even carefully curated reference data can be wrong, and without corroboration, those errors are invisible. OCR Hallucinations. Observation 5. The pipeline flagged Poland as a geographic entity connected to the Epstein network. The source document EFTA 012688833, page 17, is a blank KYC form, a Know Your Customer form with empty fields. The pre-printed field label persons/non, the beginning of persons/non-persons, was OCR'd as Poland. A blank form generated a phantom country. Observation 6. The pipeline flagged Krakow as a geographic entity appearing across 190 pages of Ghislaine Maxwell's UBS account statements. The text, Resource Management Account, a standard account header repeated on every page, was OCR'd as containing Krakow. The pipeline did not find Poland or Krakow. It hallucinated them from visual noise. These are not edge cases. These are systematic failure modes. Pre-printed labels on empty government forms. Repeated headers mangled through hundreds of pages. Both create phantom entities that propagate through named entity recognition into the entity graph and into community detection. The Retraction Standard. When the pipeline gets it wrong, the error is not quietly removed. It is formally retracted, reclassified, and preserved. Observation 5. Poland, retracted, reclassified as an OCR false positive from a blank KYC form. The full error chain is documented: how the field label was misread, how it entered the entity table, and what downstream analysis it contaminated. Observation 6. Krakow. Retracted. Same treatment. The repeated header artifact across 190 pages is documented with the specific failure mode for future prevention. Observation 1. The Robert Crumb FedEx shipment. Refuted through external research. Crumb has lived in France since 1991. The hypothesis was wrong. Retracted observations are not deleted. They are preserved because the method that produced the error is as important as the error itself. Every retraction teaches the system something about its own failure modes. Deleting errors does not make a system more accurate. It makes it less honest. Error propagation. An OCR error at stage 2, a misread character, a hallucinated word, creates a phantom entity at stage 4. That phantom entity creates a false edge in the entity graph at stage 5. The false edge distorts community detection at stage 21. The distorted community produces a false broker identification, and the false broker contaminates cross-domain synthesis at stage 25. Each error is small: 5% OCR error, 3% NER error, 5% entity resolution error, 2% network error. Individually, each is within tolerance, but errors compound multiplicatively. The formula: compound error equals 1 minus the product of 1 minus each individual error rate. 5% plus 3% plus 5% plus 2% does not equal 15%. It equals approximately 14.4%. This is why the F1 threshold exists at each stage. It limits how much error can pass through to the next stage. Without stage gates, a small upstream error becomes a large downstream distortion. Chowan completeness. The Chowan estimator is a species richness model borrowed from ecology. Biologists use it to estimate how many species exist in a habitat when they have only sampled a fraction of the population. We use it to answer a question the pipeline cannot answer on its own. How many entities exist that the pipeline has never seen? The intuition is this: if you keep finding new species every time you look, you are far from complete. If most of what you find you have seen before, you are close. The ratio of things seen once to things seen twice tells you how much remains hidden. The formula: S estimated equals S observed plus F1 squared over 2 times F2. Let me walk through the numbers. S observed, 821,633. That is the count of unique entities the pipeline has extracted across the entire corpus. F1, 197,945. These are singletons, entities that appear exactly once in the entire corpus. Nearly 1 in 4 entities, 24.1%, appears only once. That is a high singleton ratio. It means the pipeline is still discovering new entities at a significant rate. F2, 41,816. These are doubletons, entities that appear exactly twice. The calculation: 197,945 squared divided by 2 times 41,816. That gives us 468,508 additional entities estimated to exist but never observed. The result: 1,290,141 estimated total entities. The pipeline has surfaced 63.7%. 468,000 entities remain unseen. They exist in the corpus, or in the gaps where documents are missing, but the pipeline has not found them. Every finding this project presents is drawn from 63.7% of the estimated entity population. The other 36.3% is dark matter. Network topology. Leiden community detection, the constant Potts model at gamma 0.05, partitioned the entity relationship graph into 125,620 communities. Let me explain what that number means. A community is a group of entities that appear together in documents more often than they appear with entities outside the group. 125,620 of these natural groupings emerged from 29.5 million unique entity relationship pairs. Why Leiden over Louvain? Louvain is faster, but it produces what are called ghost communities, clusters that contain nodes with no internal connections. Two entities assigned to the same community that never actually co-occur in any document. Leiden has a mathematical guarantee that this cannot happen. Every node within a Leiden community can reach every other node through that community's edges. The resolution parameter, gamma, controls how fine-grained the communities are. At gamma 0.05, which sits at the center of the CPM plateau, the algorithm finds a stable partition. Moving gamma slightly higher or lower does not dramatically change the community structure. That stability is itself a form of validation. 535,318 brokers identified through BERT's structural constraint analysis. A broker is not simply a node with many connections. It is a node that bridges structural holes, connecting otherwise disconnected communities. High-degree nodes with high constraint are shadow egos, redundant to another central broker. The shadow ego filter removes them before identifying genuine brokers. The quality gate, modularity Q greater than 0.30, is now testable against this partition. Entity resolution. 2.38 million entities extracted by named entity recognition from 97.4% of the corpus entered the Splink probabilistic linkage system. They emerged as 519,000 clusters, a compression ratio of 4.6 to 1. Each cluster is a hypothesis. It says, these records, these different spellings, these different formats, these different contexts, all refer to the same real-world entity. Some clusters are obvious. Jeffrey Epstein and J. Epstein and Jeffrey Epstein. Others are subtle. Lauren Quine and Lauren Quintner. 8 garbage clusters were dissolved in a post-processing step. These were large clusters held together by weak edges, the overmerge problem from slide 11. 3,576 entities were freed from incorrect consolidation. That dissolution is itself a form of validation. The system detected its own overmerges and corrected them, not perfectly, not completely, but measurably. 519,000 hypotheses, each one subject to the F1 threshold, each one falsifiable. PELT, change point detection. 889 breakpoints, moments where the statistical properties of the entity mentioned time series changed significantly. PELT, pruned exact linear time, is an algorithm that finds the optimal segmentation of a time series into regions of different behavior. The cost function is L2, least squares. The penalty is MBIC, Modified Bayesian Information Criterion, which accounts for segment spacing and length, preventing the algorithm from flagging short-term noise as structural breaks. The calibration target. At least 85% of detected change points must align chronologically with verified historical anchors from the calibration timeline. The non-prosecution agreement signing, the arrest, the death, the consent orders, the Transparency Act. If the algorithm detects a breakpoint where no known event occurred, that is either a discovery or an artifact. Both must be investigated. And if it fails to detect a breakpoint at a known event, that tells us the event did not leave a measurable trace in this corpus. That absence is information too. 889 moments where the data changed. Each one is a question. What happened here? The compound error model. Each pipeline stage introduces its own error rate. OCR, approximately 5% on this corpus. Named entity recognition, approximately 3%. Entity resolution, approximately 5%. Network topology, approximately 2%. Individually, each is acceptable. Combined, they produce approximately 14.2% compound error, or 85.8% compound confidence. The minimum viable threshold is 85%. Below this line, findings are barred from intelligence products. They are flagged for manual review. They do not appear in any episode of this series without explicit qualification. This model is designed but not fully calibrated. The individual error rates are estimates from the validation framework, not measured values from the production pipeline. When the full Bootstrap protocol is executed, these estimates will be replaced with measured confidence intervals. Until then, they are the project's best understanding of its own uncertainty. And stating that uncertainty openly is itself a form of rigor. Most systems do not disclose what they do not know. Publishing error rates. Every episode in this series states its limitations, not in fine print, not in footnotes, alongside the findings. False positive rates. Observations 1, 5, and 6 were wrong. They are documented as wrong. False negative rates. Chow 1 estimates 36.3% of entities have never been seen. The pipeline is working with 63.7% of the estimated population. Confidence intervals. The Bootstrap protocol is designed to produce 95% confidence intervals. It is not yet executed. That distinction is stated. Single source limitations. Episode 5, the SAR, is built entirely from one document, one TD Bank suspicious activity report. Every finding in that episode carries single source risk. OCR quality. 84% of charge field values in the FedEx data were corrupted by OCR. $422,000 of overstatement was identified and corrected. A finding without an error rate is not a finding. It is a guess presented with confidence. A finding without an error rate is not a finding. It is a claim. Let that distinction settle, because this is the single most important idea in this episode. Our AI identified all the connections. That is a claim. It tells you nothing about how many connections were missed, how many were false, or how the system was tested. Entity resolution F1 equals 0.84 on 400 reviewed pairs. That is a finding. It tells you the accuracy, the sample size, and the metric. You can evaluate it. You can challenge it. You can try to reproduce it. We found everyone involved. That is a claim. It is also almost certainly false, and without a completeness estimate, there is no way to know how false. 63.7% of estimated entities observed, calculated via Chow-1 species richness estimation. That is a finding. It tells you exactly how much is missing. Our timeline is accurate. Claim. 5 of 50 calibration dates were incorrect and have been corrected. Finding. The second version is more honest, even though it admits errors because it quantifies them. The data shows links to Poland. Claim. And in this project, a false one. OCR hallucinated Poland from a blank form. Without error analysis, that hallucination would have been published as a connection. With error analysis, it was retracted. The difference between a claim and a finding is not sophistication. It is not technical vocabulary. It is honesty. A finding says, here is what we measured, here is how we measured it, and here is how often we were wrong. A claim says, trust us. Transparent science. Here is the full status of the validation framework. Every component, designed or executed, result or pending. The Bootstrap protocol, designed, not executed, pending. The F1 quality gate, designed, partially tested on sample data, not at production scale. 519,000 clusters were produced, but the formal F1 measurement against the 400-pair review set has not been completed. The modularity Q gate, designed and now testable. 125,620 communities from Leiden. The Chow-1 completeness estimator, designed and executed, 63.7%. Network topology, designed and executed, 535,318 brokers. PELT, designed and executed, 889 breakpoints. External corroboration, designed and executed across 6 domains. The compound error model, designed, not executed. The individual error rates are estimates, not measurements. A designed validation is a plan. An executed validation is evidence. This project documents both and distinguishes between them. Error log. Item 1. The Bootstrap protocol is designed but not executed. The 400 sample, 3 strata, 1000 resample protocol exists on paper. It has not been run. Item 2. The F1 quality gate has not been formally tested at production scale. Splink produced 519,000 clusters. The formal measurement of whether those clusters achieve F1 above 0.84 has not been completed. Item 3. The compound error model uses estimates, not measured values. The individual error rates per stage are projections from the validation framework design, not empirical measurements from the production pipeline. Item 4. The recall gate has not been validated. Items 5 through 8. Corrections. 5 dates wrong, corrected. 2 observations hallucinated, retracted. 1 observation refuted, reclassified. Item 9. N212JE tail number recycling is a known blind spot, documented. Items 10 and 11. Disclosed limitations. 36.3% of entities unseen. Error rates are estimates. This is what an error log looks like when the goal is truth, not persuasion. What you can do. Demand error rates. When you encounter any data-driven claim in journalism, in a government report, on social media, in an AI-generated analysis, ask 5 questions. 1. What is the error rate? Not, is it accurate? What is the specific measured error rate? 2. How was the data verified? Internal consistency checks are not enough. Was there external corroboration? 3. What is the false positive rate? Of the connections or patterns claimed, how many were tested and found to be wrong? 4. What was excluded from the analysis? What data was missing? What entities were unseen? What time periods had no coverage? 5. Were the results tested against alternative explanations? Was there an innocent hypothesis? Was it tested? You have spent this episode learning what rigorous methodology looks like: the F1 threshold, the Bootstrap protocol, the Daubert Standard, the Retraction Standard, the error log. These are not exotic tools. They are minimum standards. Hold every data-driven claim you encounter to them. Findings presented without methodology are claims, not evidence. Next, Episode 13, Convergence. When the domains connect. Cross-domain fusion, the hyper-timeline. When a wire transfer, a FedEx shipment, a flight log entry, and an email all point to the same 48-hour window. Every domain this series has examined, financial, logistics, aviation, corporate, communications, converges into a single timeline. And convergence only means something if the individual domains have been validated. If entity resolution is unreliable, connections between domains are unreliable. If temporal change points are noise, temporal convergence is noise. The method you learned in this episode is what makes that convergence trustworthy. Without 0.84, convergence is coincidence. Convergence, when the domains connect.